Introduce our speaker today, Prof. Balister, who will speak about Sentry selection. So let's start.
Okay, so this is all joint work with Bela Bolabash, Amitesh Sarkar, and Mark Walters. First of all, I'm going to describe the mathematical model and then give a little bit of introduction as to why one might be interested in it. So the model is that we're going to consider a collection of points randomly scattered in the plane. Now, these points are basically going to be some sort of sensing devices in some sort of wireless network. And for a mathematical model, we're going to model this as a Poisson process. So that means of unit intensity, which means that if you fix any area in the plane, then the number of points inside that region is going to be Poisson distributed, with the average number being the area of the region, and disjoint regions are independent. This model is very commonly used because it's very nice to analyze and it's much easier to deal with. Roughly speaking, if you want a very similar sort of model, you can think of it as being the limit as taking a box of area n, where n is very, very large, and then tossing n points uniformly at random and independently at random into this box, and then letting n tend to infinity. This is essentially the process that we have here. Okay. Whoops. Next step. We imagine that these vertices, these points, are actually sensors, and they detect events within a certain region around themselves. For this talk, I'm going to assume for simplicity that they're disks, although that's not terribly important. And I'm going to assume they all have the same radius. So each sensor just detects everything within radius r of itself. And let CR be this collection of these disks. Now, we consider a large region that we're going to be interested in, which will typically be either a large disk or a square, or more or less anything for which the boundary is sort of reasonable. So I want the boundary to be of order length root n and not too wiggly. So squares and disks are fine. And then we say that this collection of disks forms a K cover of this region if every point in the region is covered by at least K of the disks. So I'm afraid in that little picture that I drew, it's actually zero cover because there are little bits which are not actually covered at all. But if I put more disks down and covered up all the areas, you have a K cover if every point in the region is covered at least K times. And we say that this cover is K partitionable if it's the disjoint union of K single covers. So in other words, if I can partition these disks into K disjoint sets, each set of disks individually covering the whole region. And I note that an obvious implication is that if you can partition it into K covers, then obviously each point is covered at least K times. So K partitionability implies K coverage. So the application. We consider the points of our Poisson process as sensors which are deployed in a random fashion. Sn is the region to be monitored. Okay. And we want to monitor the entire region. So we want one coverage. But quite often in practice, there may be more than one coverage. We may cover the region too often. We may have more sensors than we actually need to cover the region. And on the other hand, these sensors often have batteries. These little wireless networks often have these sensors, often are very small. They have small power supply. The battery will run down. So in order to maximize the length of time for which these things operate, we want to tell most of these sensors to go to sleep and have them just wake up periodically and so only operate for a certain part of the time. Now,
Repeat please, in
So k partitionable was that I can take these disks and I can put them into k different groups. Each group on its own covers the whole region. So, so in some sense, I can specify. Well, actually, it's probably best to talk about it over here. The application is how I'm going to use k partitionability. Well, there's an obvious strategy for allowing these things to sleep for a long time, and that is to decompose them into k groups of sensors and have one sensor group in group 1 operating during time 1, sensor in group 2 operating in time 2, and so on, and when I get to k I just wrap round again. So each sensor is only active for 1 in k of the time. And in some sense this is I mean, one couldn't really do any better than that if one had k coverage, because if it's only k coverage, if it's only a k coverage, there must be a point in the region which is only seen by k sensors. So of those sensors, they're each going to have to be on average active for 1 over k of the time, because at any one time one of those k sensors has to be active. So in some sense, if you've got k coverage, you can't run the sensor network for longer than k times the battery lifetime of one sensor. On the other hand, if you have k partitionability, you can run it for k times the length of the battery life of one sensor. So the question is, what's the difference between these two concepts? Is k coverage enough to ensure k partitionability? Now, I said that if you could partition them into k groups, you've got k coverage. But what about the converse? What happens if we know it's k coverage, is k covered? Can we partition them into k groups? And the answer, of course, is no, in general. So let's give some examples. So this is just deterministically, there's no randomness involved. If the sensors were sensing some arbitrary subset of the plane, I mean, this is slightly crazy, but let's say it was just detecting an arbitrary subset of points, then 1,000,000 coverage is not necessarily enough to imply two partitionability. So you could have these regions covering every point 1,000,000 times, and yet you still can't split them up into two groups, each of which covers just once. And there are some very simple examples of this. So this is a slightly abstract example, but it gives the point. If our ground set were indexed by the subsets of 1 up to 2k minus 1 of size k, and the disk just covered all the k subsets containing a particular point I, so disk I covers all the subsets which contain I, then it's pretty clear that every k subset is in k of the disks. I mean, it's one disk for every one of its elements. But unfortunately, if I try to split those disks into two groups, one of those groups will contain k disks, and if I take the indices for each of those k disks and put them together to form a set, it's not covered. So I can't split it up into two groups even. Okay, so that's really rather ridiculous to have an arbitrary subset of the plane. So let's be a little bit more reasonable. Let's say convex sets. So what happens if the sensing regions are convex? Well, that doesn't help you.
Sorry, maybe you shall give the picture of this for this case when you have million disks in one place and you cannot have the partition.
I can't draw it with disks, I'm afraid. I can do it with arbitrary subsets, but those are a bit different. What?
For disks, you cannot give the picture.
I can't myself draw the picture because I don't know whether it exists for disks. But I'll give some examples with disks in a moment, but not quite so extreme. Okay, so for convex doesn't actually help you at all, and there's this rather silly little construction. What you can do is you can take a polygon, and then this is supposed to be a square, and then you just round off some of the corners to make it into a circle. And if you have a set like 2 and 4, you leave the corners, it's like a cogwheel, except I've left in cogs number 2 and 4 and cut off number 1 and 3. And if I put loads of those down on top of each other, and then put lots of half planes around the square, off in all the different directions, I can actually translate a general set system counterexample into a convex set example. Because what I do is that this is a disk covering here and here, but not here and here, and similarly with loads of others. And if I did this instead of with 4 corners, if I did it with 1,000,000 corners, I can basically reproduce an arbitrary set system counterexample. So, I mean, it's just slightly artificial construction, but deterministically you can't do anything with convex sets.
But if you just consider on the plane just squares which are oriented this way, squares of fixed size, so 1 by 1.
1 by 1.
So then the squares, what is the minimal k?
Ooh, I think that's
idea?
not known. Even that one's not known.
Even that.
That's not known. Disk regions, this is the embarrassing one. It's not known. It's unknown if k coverage implies 2 partitionability for any k bigger than 3. 3 is definitely not. Sorry, that's a mistake. Sorry. K greater or equal to 3. 2 coverage does not imply 2 partitionability. Sorry, that's a mistake. In 3D, it is known that any k coverage does not imply 2 partitionability. So, a bit like the convex sets in 2 dimensions, disks don't work. So, the amount of knowledge we have about this is remarkably little. So, here is an example.
Sorry, maybe you said for disks, it's not known that any finite number.
Yeah, it's not known for any finite number.
It was announced that it was, but that was 10 years ago.
And apparently the proof collapsed. So here's the obvious example. I'll draw this. It's on the board. It's on the screen as well, but I'll just draw it just to give a quick idea of how do you do 2 partitionability, 2 coverage, but not 2 partitionability with disks. Well, if you just take 3 disks like this, how are they covered? This is covered 3, 2, 2, 2, 1, 1, 1. Okay, that's the coverage. Now, if you were to sneak some disks over in here, here, and here, and then put loads of disks on the outside, away from this region, you could bump up the coverage to 2 everywhere. But you can't partition it into 2 groups, because this group is in disks A and B, this is in A and C, this is A, and this is in B and C, and it doesn't matter how I partition A, B, and C into 2 groups, one of these 2 regions is going to fail. So that's actually the first picture, except it's not quite so obvious. But there are 3 regions marked by the black dots, such that each one is covered by 2 of the circles 1, 2, and 3. And the whole thing can be extended so the whole plane is 2 covered, but if you partition them anyway, 2 of the 1, 2, and 3 have to be in one group, 1 has to be in the other, and then there's an uncovered region. And the one on the right is actually another example with 5 regions. So the picture here is you take a pentagon, and then you draw disks which cover 5 disks, which each cover 2 of them, and also cover the center, and so on. And once again, you can fill it out to make it to cover the whole region. But if you partition these 5 disks into 2 groups, one of those groups has got to have at least 3 in it. The other one has to have at most 2. And with only 2 of these, you can't cover all 5 points. So one of the areas is going to get uncovered. could also do this with 7 points, 9 points, and so on, but there you, in order to cover the middle properly, you actually need the curvature of the circle. These two examples are quite nice, and that's actually important later on, that they don't rely on the curvature of the circles. You could do it with half planes, and it's still the same example.
Sorry, everywhere you have the points where three spheres were connected.
So, which here?
Here, yes.
Here, you've got, this is
You have the point where three squares
Yeah.
have the common point.
yes, you've got a middle bit which is 3 covered. But that doesn't cause any trouble.
You have here these special points which are very rare in the usual pictures. When three points and three spheres have the common point.
Yes. Yes.
Is it possible to have the same picture without such effects?
Oh, sorry. No, this actually can go over it. That's okay. That just has to cover it. It doesn't have to actually intersect it. Okay. Yes, I should say, because we're dealing with the probabilistic setting, I'm going to assume that no probability 0 things occur later on. Okay. But, sorry, as I said, it's not known whether 3 coverage by disks implies 2 partitionability. Although we can't find a counterexample. Okay, later on we're going to be interested in half planes, which actually we do know the answer for. If you 3 cover by half planes, then it is 2 partitionability. It is 2 partitionable. This is actually a consequence of Helly's theorem, or is a simple 5-minute exercise. Helly's theorem says that if you've got a bunch of convex sets, any 3 of which intersect, then they all intersect. Apply it to the complement of the half plane and translate it, and that turns out to be exactly equivalent to the statement that, for half planes at least, that if the space is covered by half planes, then you can find 3 of them that cover. If it's 3 covered by half planes, then it follows as a fairly simple exercise. Okay, so the theorem is that if you have a finite k cover of r squared by half planes, then you can actually, it's k over 2 partitionable. On the other hand, there exist examples which are not more than about 2/3 k partitionable. So the example why you can't do better than 2/3 is actually fairly easy, so I'll draw that again. If you just take a center point and just cover it all the way around with n planes at equal angles all the way around, then half planes all the way around. Then just a very, very quick calculation. If they're all at equal angles, roughly every point is covered by about half of them. But on the other hand, you need 3 to cover the whole plane. So only, it's sort of n over 3 partitionable, but it's an n over 2 cover. So the level of partitionability is sort of 2/3 of the coverage. For the other side, k over 2 partitionable, k over 3 should be fairly obvious from the example. If you've got a lot of coverage and you can get 2 partitionability, then what you can do is you can actually, from Helly's theorem, pick out 3 actual half planes that do the covering, take them away, and then just repeat. And the k over 2 is just a slight, subtle improvement on that. Okay, but this leaves some interesting questions, like what's the minimum level of coverage by half planes which give k partitionability? And of course, going back, what about the disks, which we know nothing about? Okay, so this is so far all deterministic stuff. So the question is, now we're going to go back to the probabilistic setting. Since we know absolutely nothing or almost nothing about the deterministic case, let's make it random, and then we can actually start proving things. So, we want to show, and what the main result is that actually, in most cases, if it's K covered, if it's got K coverage, then it does have K partitionability. So this is the positive statement. So the first question is, when do we have K coverage in this Poisson process? Well, so remember my original area, my disk, my big area that I was covering was of area n, and the Poisson is a process of intensity 1. So typically there will be n sensors within the region. How much do I need? What radius of disk do I need so that this will actually cover? And there's a theorem by Hall in 85 which pretty much answers this, and that is that the area of the sensor disks needs to be about log n. Well, log n plus k times log n, and if you add a growing term to that, it'll be a k cover with probability tending to 1. If you add a negative thing, then it will actually not be a k cover with probability 1. We can actually strengthen the result a little bit, beef it up, so and give a more quantitative result, which is that if pi r squared is exactly log n, that's k log n plus some function, then the probability that it k covers tends to e to the minus f over k minus 1 factorial, plus some small error terms which tend to 0 as n tends to infinity.
Could you repeat notation? So Sn is a square, n times n.
Sn is a square or a circle. It's just our big region.
Yeah.
Okay, of area n. That's the important thing.
And R?
R is the sensor disk radius. So R is the radius of the little sensor disks, and those are disks. N is just the area of the big region. Okay. And in some sense, the idea is you need log n because there's basically if you consider a single point in your region, what's the probability of it not being covered? Well, it's not covered if there's no sense of within distance r. And for a Poisson process, if you've got area pi r squared, then the chances of then being nothing there is e to the minus pi r squared. It's probability of Poisson being 0. If the Poisson just has to be less than k for failure, that is where you get the k log n term. So the idea is that pi r squared, ether pi r squared should be around about n. Okay. And as I said, this theorem is a sort of slight refinement of it. We can actually get some pretty good, pretty accurate assessment, and I'll show you later on roughly how accurate it is, of what's the probability of K coverage. So the purpose of this basically is to tell you roughly in what region, how many points do we have? And the answer is the number of points we have, what's the, or equivalently, what's the radius of the disk? The radius of the disk is essentially so that the area of the disk is about log n. That's the sort of order of magnitude. So, actually, this theorem here, I can give you a very quick sketch of roughly why this is true. So this is a brief sketch as to why this formula is correct. So the idea is what we do is we count intersections of boundaries of disks. So we've got loads of disks, and every once in a while they intersect. And we're going to count the intersections. So how many intersections are there? Well, you've got n disks. Okay. So let's pick one disk. How many intersections are there on the boundary of the disk? Well, for two disks to intersect, they have to be within distance 2r of one another. Because if each disk is of radius r, you need them within 2r to intersect. Which means that typically there are 4 pi r squared disks, because the Poisson is intensity 1, 4 pi r squared disks intersect a given disk on average. Of course, when two circles intersect, they intersect in 2 points. But on the other hand, there's, if I count them like this, if I look over all disks and look at all the intersections of it, of course, each intersection occurs in 2 disks, so I overcount. So that factor of 2 goes away. So basically, the number of intersections is basically 4 pi r squared for every disk, and there are n disks. So it's 4 pi r squared n. And since pi r squared is about log n, that's about 4n log n. Okay, and then what's the chances of this intersection not being k-covered? Well, it doesn't matter. I mean, it's independent of its existence. It's independent of the 2 points that caused this. So I'm asking whether this region here, which is not quite covered by these 2 disks, whether that's covered. That's what I mean by the intersection not being covered. Well, the number of times it's covered is given by a Poisson variable of mean pi r squared, because that's just the number of sensors within distance r again. And then you just do this calculation, you plug in the formula that I gave on the previous slide into that, and you get 4 e to the minus f over k minus 1 factorial. But of course this is not the answer, because all I'm doing is counting the number of inadequately covered intersection points. And these are not independent. They're not independent because, let's draw it over here. It's not independent because if I have one intersection point which is not adequately covered, then there are going to be others which are, I mean, just follow around the polygon. There are going to be others which are not adequately covered. So there's no way that the number of uncovered intersection points is independent of each other. I mean, there's a minimum of 3, in fact. So the number of uncovered intersection points is not, can't take every possible value. It can't take the values 1 and 2, for example. It can either be 0 or at least 3. So it's certainly not given by a Poisson distribution or anything nice and simple like that. But there's a way of counting the uncovered regions, or inadequately covered regions, so regions that are not k-covered. So the idea is this: it's not too hard to show that in the regime we're talking about, where there's roughly each disk is has area about log n, so each point is typically covered about log n times. Typically the regions which are not adequately covered, most of the region is log n covered. It's covered an immense number of times. So what happens when something is not k-covered is that's actually very, very rare. And it usually occurs only in very, very small regions. So the regions that are not adequately covered are very small regions whose boundaries look like boundaries of circles. But those circles are much, much bigger. So in fact, they look like small polygons, because on this scale, the sides are almost straight. It's a fairly straightforward calculation that the average angle of intersection between 2 disks is actually 90 degrees. And just do the integral. And it's independent of whether or not this intersection is covered by other disks. So a little bit of geometry, the sum of the exterior angles in a polygon adding up to 360 degrees, means that on average these polygons have 4 sides. Now I'm not saying they do have 4 sides, there are triangles, there are pentagons, whatever, but on average they have 4 sides, which is actually quite surprising. I mean, many people would think that, you know, once these regions are very small, they're more likely to be a triangle than anything else, but in fact that's not true. So typically, whenever you get one insufficiently covered region, intersection point, there are usually 4 of them on average. So to get the average number of uncovered regions, you divide by 4, and so you get e to the minus f over k minus 1 factorial. And then there's a standard method called the Chen-Stein method, which shows that these are more or less independent of each other, and so they occur with the regions, not the intersections, but the regions occur with a Poisson distribution, and therefore the probability of there not being any of them is e to the minus that, so e to the average number of them. So it's sort of interesting that one can actually come up with a fairly precise result for the probability that there is a point somewhere which is not k-covered. Okay. But that's not the purpose of the talk. The purpose of the talk is to talk about partitionability. So the stuff I've done tells you pretty precisely what the R and what the N, what relationship they have to have some chance of K coverage. So now we're going to ask about K partitionability. And this is a bit harder. It's quite a bit harder. So I just state the results here, and I'll talk a little bit about how we got them. And the result is that regardless of the values of R and N, and for any fixed K, the probability that you have a K cover but it's not K partitionable is little o of 1. It's in fact less than a constant over log n.
What are the conditions again? So R, N, and K, what are the limits?
Yeah, so in other words, there's for any values of R, N, and K, I mean there's a constant depending on K, such that for any values of R, N, and K, the probability that if I put N, so plot on N points down in a region of area N, and put disk around them of radius R, the probability that it does K cover but does not K partition, so it's the difference of the two, is bounded by that constant depending on K over log N. But the constant doesn't depend on R or N.
How does R depend on N? Yeah,
this is uniform in R.
How does R depend on N?
It's uniform. This is true regardless of R. There's only a small window of R for which this is not trivial. I mean, if R is too small, then it just never K covers, so it's got no chance. And if R is huge, then it's bound to K partition. So this doesn't happen. I mean, there's only a window where it's sort of reasonable that one could happen, but the other one doesn't.
Second theorem.
Okay. The second theorem is, this is sharp, but of course this is only sharp in a window. This is sharp that if I actually pick pi r squared to be exactly log n plus k log n, actually you could throw in a constant at the end, it wouldn't make any difference, then the probability that it k covers but does not k partition is at least a constant over log n. So now, in other words, 1 over log n is the right error. Okay.
And if R is at most half of log n, for instance, R squared, or if R is essentially R squared is essentially smaller than log L,
then it's not going to K cover. So if pi r squared is a lot less than log n, then it's no chance of covering at all. So both of these events don't occur. I mean, this event doesn't occur because it doesn't K cover. I'm looking at the difference between it K covering and it K partitioning. If it doesn't K cover, then I'm okay. If I throw in so much that it's obviously K partitions, then I'm okay. It's only really in the middle where there's an issue.
and if R is essentially bigger than log n, say two logs,
then it's just easily K partitions with very, very high probability. I mean, you can imagine just throwing the or increasing R or throwing the disks in one by one. I'll talk about this in a moment. At first, it doesn't cover at all. Eventually, it covers by such a big margin that, of course, it's going to partition into K groups. So the question is, as you go along, is there a point where it's much more likely to do one but not the other? At the end, I'll draw a graph showing you the distribution, I mean, to show you the probability function. So you can see how close these are. So really this is the probability that K covers minus the probability that it's K partitions, because one event is contained inside the other. Okay. Right, okay, so there's some, just a quick sketch of the ideas. Now, in all of this stuff, the details tend to get rather technical, but I'd just like to give you a rough idea of what are the main ingredients for the proof. So, first of all, there's the Lovis local lemma will deal with everything as long as everything were at least sort of K log n covered. So in other words, if you had massive coverage, then of course it seems reasonable that one can partition them into K groups. And the Lovis local lemma allows us to do that. Unfortunately, it only allows us to do that when we get up to quite a lot larger than K. You have to go up to a function of n before we can use this to guarantee that it can be partitioned. And so this isn't really strong enough. Okay, but we can therefore assume that we're in the region where it's not 3K log n covered. I mean, there are going to be regions where it's not that heavily covered. If it's that heavily covered everywhere, then we're done. So we only need to look at the areas which are less than this level of coverage. And the reason is that if we can deal with these if we can deal with the regions which are not heavily covered, then in fact the Lovis local lemma you can expand it and deal with the rest. And it turns out that in this sort of range, what happens is that the areas which are less than 3K log n whatever covered are actually very, very small. So you have this large region of area n, and you've just got this tiny little dot somewhere, tiny little area where the coverage, so typically the coverage is about log n, and in just a few little points it drops a lot below that, and it's got to drop a lot below that. I mean, it's got to go from log n down to log n. So there are just tiny little areas where it's not very heavily covered. And these are, one can show quite easily, are actually very, very small regions. They can actually be covered by very small disks. And these disks are isolated and a long way away from each other with very high probability. And then the idea is that what we're going to do is we're going to zoom into these little disks, color them in some clever way so as to partition them into K groups. So, I mean, partitioning into K groups is sometimes called coloring. You just color them with K different colors. That's partitioning into K groups. Deal with these little groups on their own, and then stand back and let Lovis local lemma deal with the rest. So that's the strategy. Okay, but these disks are so small that any circle sensor region crossing this disk looks like a half plane, because these things are much, much smaller than the sensor region. So at this scale, the sensing regions are half planes, and we can deal with half planes. So that's I mean, in fact, it didn't need to be a disk. It just had to be something with bounded radius of curvature. I mean, the disk is in some sense irrelevant here. If you look at it on a small enough scale, the boundary looks flat. Okay, I'm not sure how much of this detail I want to go into, but inside each DI, I'm going to look at the regions which are actually less than about 3K covered. I'll call those lightly covered. These are the really bad areas. These are ones where it's getting very dodgy. I mean, can we split these? And the rest of the DIs I'll just call well covered. So typically we've got lightly covered, that's less than 3K. We've got well covered, which is above 3K but can include things which are less than 3K log n. And then outside the disk, it's very well covered, so at least 3K log n. So there's three levels. There's the sparse little bits. There's the disks contain things which are sort of moderately well covered, and then outside the disk, it's very, very well covered. Okay. And it's not too hard to show. Well, I mean, one needs a little bit of work, but if you look at these lightly covered regions, actually typically, I mean, we don't need to prove this, but typically each disk only contains one of these usually. So you have this less than 3K covered regions, very, very small. But you may have several of them inside this DI. And usually what you would expect to happen, so these things are K covered. We know that they are K covered. We're assuming everything's K covered. It's usual that they're K covered by the same set of K disks. I mean, think, these disks are enormous. The sensing disks are enormous. Here's the boundary of a sensing disk. It's usually going to completely cover it by miles or miss it by miles. Okay. Actually, it's not going to go through the regions, but that's like that. It's very, very unlikely to cover one of the regions but not the other. Okay, but that can happen. But it's not going to happen very often. So you know it's K covered. It's usually, in fact, K covered by the same K disks. If it's not covered by the same K disks, then at least K-1 disks should be in common. And then just for the last one, it needs different disks. But it gets progressively less likely, I mean, it's very much less likely that they only have K-2 disks in common, or K-3 or K-4. It gets much, much less likely. So typically, there are K-1 disks which just cover the whole lot, and that gives you K-1 of the coverage. We know we've got K coverage, but K-1 of them is just with single disks which just cover them all. And one can show that that fails with probability at most 1 over log n. And that's where the 1 over log n comes from. Since we're assuming K coverage, we can find another bunch of sensors which do the last coverage. In fact, you can do 3 of them because they look like half planes. And then, okay, there's a little induction argument that what you can do is you can partition them into K covers by taking one of the planes that covers all the very lightly covered regions, perhaps sticking on a few other half planes to cover the whole of DI, because those might not cover the whole of DI, and then do this sort of K times, and one can show, a little bit of hand waving here, but one can show that one can do this, and that we can actually split these into K distinct covers, each of which only has 3 disks. Okay, so we haven't taken too many disks away. But it's the whole thing is that the obstructions are very, very small. If you look on a very small scale, disks look like half planes, and we know a little bit about half planes. Okay.
Sorry.
Yeah.
Sorry. Is it true that if we should look at this picture from very large distance,
Yeah.
these points will be almost points on our plane?
Yeah. I gave the scale. I gave the scale. It's essentially 1 over log n.
Okay.
Root log n.
Correlations, the distance between these
Yeah.
non-covered, non-partitioned points
Yeah.
in this scaling will be not exponential. It's not Poissonic.
Yeah.
It will be maybe polynomial.
The disks we know are a long way away from each other, more than many sensor diameters away, so they are essentially independent.
Yeah,
The DIs are independent of each other because they're too far away from each other. They're not covered by the same disk.
But they covered the same disks, as you said.
Oh no! Within each DI, all the very lightly covered regions are covered by at least K-1 just cover the whole lot.
So why they are independent?
No, those are dependent. Those are dependent. But between ones, so if you look at it, most of the areas, big sea of very, very heavily covered stuff. There's a few little isolated dots where it's not very heavily covered. These can be covered in little tiny disks. And then the tiny little disks we just do deterministically, using the fact that the coverage looks like half planes. and that we got k minus 1 of the coverage is given to us in single disks. So the point is the dealing with the DIs is almost deterministic. I mean, we need the disks to be covered, there to be k minus 1 disks, sensor disks which cover the DIs, but the rest of it is essentially looks like half planes, and we know that if we've got coverage, we can find 3 half planes that will cover the whole lot. So we can find, I mean, you know, that bit's sort of deterministic inside the DIs. The DIs themselves are very, very heavily separated, so they're independent. I mean, I'm skipping over lots of technical details, but this is the basic idea. Okay, yeah. So there's a little deterministic bit at the end. Okay, so why does this? So the proof goes through, and you get this result. So what are the obstructions? What are the things that go wrong? The thing that goes wrong is if you don't have these small little areas covered by k minus 1 common disks. What goes wrong is if they're covered by k minus 2 disks, and the remaining 2 levels of coverage are one of these configurations. Okay, well, I mean, these are the sorts of things that one would expect. So if one actually works out the probability of those configurations occurring, you find that in the worst case it is about constant over log n, which was the second theorem. So if you just write down what's the probability I get that somewhere, and you find it's constant over log n. Okay, and as I said, the most common obstructions arise from k minus 2 of the coverage is given to you free by big disks covering everything, but the last 2 levels of coverage are these 2 covers that can't be split into 2 groups. For the other k minus 2 groups, it's easy. You just got 1 disk is just needed on each one in this area. But the last couple of coverage causes you trouble. Okay, and just to finish off, we can actually, that constant in that theorem, one could theoretically actually calculate, because it turns out that these are actually the only configurations that occur at this level. So in other words, occur with probability order 1 over log n. Everything else occurs with probability more like 1 over log n squared. Now, everything else is much, much less likely. Anything else which goes wrong is much less likely. And here's that theorem. I just write it out a little bit more carefully. So we say a C3 configuration is a configuration in the first picture, which I just drew over here, where you've got 3 two-covered regions, here, here, and here. A1, A2, A3, which are covered by half planes, or these disks. One of them is covered by 1 and 2, one of them is covered by 2 and 3, one of them is covered by 3 and 1. And you can't split them. A C5 configuration is the same thing as this. It's where you've got 5 two-covered regions and a whole bunch of half planes that cover exactly 2 of them, and you can't split them. And the theorem, which is completely deterministically, that if you have a finite 2 cover of r squared by half planes this time, which at this scale is basically what we're looking at, that is not 2 partitionable, then it has to have one of these 2 configurations in. So going back to the sensor picture, the most likely by a long stretch, the most likely chances of you failing to k-partition your k-covered region is because you've got one of these configurations with perhaps another k minus 2 disks right over the whole lot at some point in the picture. And you don't get a C7 or C9 or anything like that because that's just sort of geometrically impossible. So that's actually nice. There are really only 2 of these things that happen. You try and draw this with 7 points, you can't cover the center. It doesn't work. Okay, so just to show that you can actually push this result a little bit further and actually have some stopping time results. So the idea is there's 2 stopping time results that one can have. So what you can do is you can put the endpoints down in your region according to a Poisson process, and then have the sensor have the R change, so have the R growing. So the sensor regions around each point just grow and grow and grow until you get K coverage. This will happen at some point. And it turns out that with high probability, you get K partitionability exactly at the same point that you get K coverage. So in other words, the last little point that disappears, which wasn't K covered, that disappears as the circles get larger, as the sensor regions get larger, the moment that happens, it's actually K partitionable. There's no gap. So sort of the worst obstruction to K partitionability is the fact that it doesn't actually K cover. And the second theorem, which is a bit harder to explain, but is the other way around. Suppose I fix the radius, I take my region, and then just throw in points at random. So in other words, I sort of increase the n in some sense. So what I do is I put uniformly at random points, one by one, into this region. Actually, the region has to be a little bit bigger because I should have said that at the beginning. In order to avoid boundary effects, the deployment region, actually the sensors outside the region also matter, because otherwise the boundary tends to get uncovered. So I don't want to deal with boundaries here, so I try to avoid that. So I actually deploy them in a slightly larger region. And then with probability tending to 1, the minimum n, so in other words, the first sensor that you put down there that causes it to be K covered actually also causes it to be K partitionable. So once again, this is a sort of stopping time result. You get partitionability as soon as you get K coverage. Okay, and here's some pictures. So how do I have to describe what these are? So here's some graphs. Forget the R. The radius was about 1 over 128 of the root n, I think, of the linear dimensions. And what I did was I just put more and more points in. So along the axis is n. It's like throwing in more points, and the radius is fixed and is quite small. So actually, I think it's a torus of 1 by 1. The radius of the disks is 1 over 128, and I just put more and more points in until certain things happen. But it's essentially the same model. And for k equals 1, which is the first couple of lines, the red line is the point at which you get coverage. The green line, which you can't see, is the case at which you get 1 partitionability. Why is this? Well, if you've got 1 coverage, you can partition them into 1 group. I mean, there's no difference. Okay. And the blue is the estimate I had from that theorem, the e to the minus f of n thing, of when you're supposed to get it. There's a slight discrepancy between the prediction and there's some error terms here. Okay, now let's look at k equals 2. So red line is the probability that you get 2 coverage. The green line is the probability that you get 2 partitionability. Can you see the difference? Just about. They are incredibly close. The chances of, so over here, you don't get either. Over here, you get both. There's a small vertical gap of about 1 over log n. But it's incredibly small. You don't really see it. I mean, n's pretty big. And then this is for 3. And the red is partitional, red is coverage, green is partitionability, blue is the estimate. The estimates aren't quite so good on these. This is k equals 4, and this is at 5 coverage, 5 partitionability. Even at 5 coverage and 5 partitionability, there's not an awful lot of difference. You know, when you get one, you tend to get the other. I mean, the difference is growing a little bit because of k, as k goes up. But even at k equals 5, there's not much difference. Okay, and that's it. I think I'll stop there.
I didn't understand the answer. So suppose we are in this interesting region when we have K coverage, but we haven't K partitions.
Yeah.
And we see quite in large, we see some points. The distance between them is quite large, where we haven't these K partitions.
Yes.
And if we shall look at these points from large distance, we shall see only one point. We will not see these squares, but quite clearly that they will be the points. Is the points are Poisson field or something different?
Yes, except since the probability of having any of the expected number of them is essentially 1 over log n, you're not going to see very many. But yes.
Yes.
Yes, I mean, with probability 1 over log n, you'll see one of them. With probability half 1 over log n squared, you'll see 2 of them.
So they're independent.
Yes, these little di's are very, very far, very separated. And so, yes, they are actually, to all intents and purposes, independent. It's very unlikely that 2 of them will occur close to each other.
One might, it might seem natural to ask about some sort of equitable partition. I mean, you might want companies of sentries of roughly the same size guarding at any given time. Can you say anything about equitable K partitionability?
That's a good question. We haven't really looked at that. Perhaps I should have said it's, the reason, of course, it's called sentry selection is suppose each group is a bunch of sentries that are guarding over the region. Yes, in reality, you don't just want to partition it into K groups, you actually want to make the groups small. I mean, what we're doing here is we're maximizing the lifetime of the network by using each sensor only one of the K at a time. But it seems rather ridiculous to be using millions of sensors when we only need one. I mean, so yes, we haven't actually optimized the number of sensors in each group. So what you could do is you say there should actually be K plus 1 groups. There should be K groups, each of which cover, and there should be one group which you can just throw away and say, I'm not going to use them at all. But we haven't, and you want to sort of maximize the number you don't use at all. But we haven't actually looked at that. Yeah.
So in the randomized model, Poisson model, you have this sort of inflation. The radius is like log n at least, right? And it just, I was wondering back to the deterministic setting. It seems like, just to cover, you pay a big price when you go random. And can you say anything back to the deterministic layouts where you might have a more regular kind of deployment?
Well, if you knew what the deployment was, then presumably you could figure out whether or not it K covered. This is difficult to formulate a sort of sensible question. One of the reasons you think that Poisson might be more applicable is because often with these sensors you have failure rates. So the idea is that you might deploy them in a nice regular grid, but then a couple of years down the line, half of them have failed, and so you've got a little bit more like a Poisson process at the end, because if a very large proportion of them fail. But yes, there are questions about what happens if it's not quite as bad as this, and you do have some sort of uniformity. The difficult bit is to sort of formulate a question which is
well,
easy
I guess
to
I was
work
thinking, you were saying at the beginning that coverage and partitionability are two different things, right?
Yeah.
And you're paying a big price with the random approach for both,
Yeah.
and you get both.
Yeah.
But what if I said, okay, I'll get 2K coverage, or is there some factor by which I could, overcover deterministically to get back to
Well,
some?
that's what I had at the beginning.
Oh, right.
We
That's the
don't
key
know
one.
that for disks. That's the
Right.
problem.
I
We
see.
don't know that if we have 1 million coverage,
Yeah.
one suspects that that's enough to partition, but we don't know this.
Right. Okay, so it's just, and there's nothing you can get out of this probabilistic analysis that might help with that.
Really, no.
Yeah.
Except the Lova's local lemma, of course, is useful there as well.
Yes, okay, that's worth pointing out. If you had 1 million coverage, but you never had a point which was, say, 2 to the million covered. I mean, in other words, if there's an upper and lower bound, then the lowest local lemma gives it to you.
Yeah.
But the problem is, you can easily come up with situations where lots of these disks gang up on places and then cause trouble. Well, at least theoretically they could. We don't know exact examples. Yeah.
You indicated that your interest in K partitionability was so that you could turn these things on and off and only run them 1K for but that's kind of what would be called a greedy control strategy, right? Where you've got these guys are on and then these guys are on.
It's a very naive, very
Is there, if I have K coverage, is there possibly a control strategy so that each sensor is still on at most 1/K at the time?
Well, basically the problem is, if you look at these, this counter example, I don't think you can do it for that, because of these 3 sensors, you need 2 of them operating at any one time. So you're right, the partition into K groups is incredibly greedy, but we see from the proof that the obstructions to this obstruct everything. So, yeah.
Then let me turn my question around. That can you find an upper bound on the maximum average amount of time that you would have to run a sensor to get?
Well, the average is basically just for K coverage, because we know with only probability 1/log(n) you fail. So I mean that's the moral of the story. We actually usually do get the K partitionability, so we don't have to worry about it. It's only very rarely that we have to worry about it. Of course, if you're looking at very rare events, then rare events could include much worse things happening. I mean, we don't know. Yeah.
Okay.
So we are close to the question of conditional probability. Assume we have K coverage.
Yeah.
Coverage. What can you say for conditional probability that we have K partition?
Oh, from
Condition we have K coverage.
Yeah, it should be 1/log(n). It should be. I mean, assuming it's Poisson, and then you condition on it being K covered. If you're anywhere in the region where K covered is remotely likely, so in other words, if the conditioning event is at all plausible, then it's constant over log(n). I think it's not true if you go right the way down. So in other words, if I put only enough sensors so that it could just theoretically K cover, and then you condition on this absurdly unlikely event, then it might not. Then that's a different story. But if you're in anything remotely like the region where this is the event that it K covers is actually at all credible,
R is small.
then it's whatever.
So it's not of interest if R is big. When R tends to 0, this will
Well, if
go.
R tends to 0, then you find yourself conditioning
So
on
Ray-
the fact
Ray
that
wins,
that you've got a sort of hexagonal lattice or something. I mean, because that's the only way of doing it with that number of disks. And that's sort of a very different question.
What did you say was 1/log(n)?
The condition, so I did the difference in probabilities. If you do the conditional probability of failure of partitionability condition on the K coverage, and if the probability of the K coverage is at all reasonable, like actually even probably 1/n would be okay, then it's going to be 1/log(n). But if you go right down to very small n, I mean, if you go right to really implausible situations, then that's not going to be true, because you're forcing the disk into extremely peculiar configurations.
You've said that things become worse if you increase K. So what happens if, for example, I required K to be log(n)?
I haven't really considered that very much. I think what happens, yes, the constant over log(n) is getting worse as K gets bigger. Well, one does know that if K is very large, then you're probably better off just using the lowest local lemma, because that actually will give you a decent answer for very large I mean, if once k gets up to sort of log n, it seems like the locus local lemma is the correct tool to use. I mean, we're not sure about what happens if it's log log n or log n or whatever. I mean, there might be some question in between, but at high levels, locus local lemma is more or less giving you the optimum.
So the constant depending on k, is there any hint as to how it might depend on k? Or
We didn't work it out, but I'm sure you can. I mean, essentially, you know what the bad configurations are, so you should be able to work it out. And you could probably go through the proof and get the upper bound as well. I don't think that's. I think that's just a pain, and you could just do it, but we haven't. Yeah. Yeah.
If you're interested in this as a way of picking sentries, is the way of picking sentries in the end at all constructive? So you know that you have k-precision ability, can you construct it?
The answer is, I believe, actually is yes. Because what we do inside the DIs is completely deterministic. And so the only question is what you do with the local lemma on the rest of it. So in other words, you've got a deterministic bit way of doing the difficult bits. Okay? And then the only question is, how do you do the bits where it's covered a billion times? Which in some senses seems like a silly question, because that's the bit which should be easy. So what you need is, but what we use is the locus local lemma, so you need a method of doing the locus local lemma. There's not I don't think it's a deterministic way of doing it, but there is a probabilistic method of algorithm for constructing solutions for that.
It is de-randomized.
So it can be de-randomized.
Yeah,
okay. So yes, there is. Yeah. Yeah. Okay.
No other questions? Let us